Hello everyone. In this module, we are going to study some of the basic concepts underlying mass spectrometry with respect to molecular ion, base peak, metastable ion, nitrogen rule, and ring rule. We will study one by one in detail. First one, let us take up the molecular ion. We have studied in the last two modules that whenever you take a molecule and hit that molecule with a highly energetic electrons, then the molecule will lose an electron and that becomes radical cation. So along with the radical cation, two more electrons will be found. That means the energetic electrons are still present. Those energetic electrons will further decompose the molecular ion into daughter ions or fragment ions. We shall not consider about fragment ions as far as this class is concerned. We shall mainly concentrate on the molecular ion. It is represented by M plus radical. This is called radical cation. Here M refers to any molecule. We know that in mass spectrometry, any molecule as such cannot be subjected for, because the molecule has to be first vaporized. That means the molecule should be in the vapor state, which is the prerequisite for the mass spectrometry. So when you take the vapor phase of an organic compound and bombard it with an electron of sufficient energy, an electron will be removed from the molecule, which results in the formation of the molecular ion. So this is how it is represented, M plus radical. It is also called M radical cation. They usually, what kind of systems will show molecular ion? Almost all classes of organic compounds known, they will show this molecular ion. Say for example, if it is aromatic system, then the highly occupied orbital of the aromatic system, and if there is any heteroatoms like oxygen and nitrogen, then there will be non-bonding pair of electrons on those heteroatoms, and they will that is the tendency for the losing electron from those systems. If there is any unsaturated system like alkene or alkyne, so an electron from the pi bond of the multiple bond or a triple bond is usually lost. And what if there is no pi bond? What if there is no heteroatom? That is the case of alkanes. Even in alkanes, you will see that the ionization between CC bond and CH bond takes place. So this is the ionization between CC sigma bond, and this is the ionization between CH single bond. The overall formation of molecular ion is shown in this equation. You take any molecule, you bombard with the sufficiently high energetic electron, then an electron will be lost from the molecule to form radical cation. So along with this electron, the electron from the molecule will also join to form two electrons. So this is the representation of different classes of organic compounds. This is the general equation. Here M is the molecule present in the vapor phase. When it is bombarded with highly energetic electrons, it is going to lose an electron to form the molecular ion. Along with that, two electrons will be formed. When we take the aromatic system, say benzene, there are three pi bonds or 6 pi electrons. When it is bombarded with the fast energetic electrons, say 70 electron volts, one of the pi electrons will be lost from benzene, which is represented like this. But still benzene will be having pi electrons, but one electron is lost. Instead of writing the resonating structure, we can just write the benzene, and on the top of that or superscript, you should write the radical cation plus 2e. If you take alcohol, we know that in alcohol, oxygen is the heteroatom. Oxygen will have two pairs of non-bonding electrons. So one of the non-bonding electron will contribute to the formation of the molecular ion. Here, in this oxygen, from this lone pair, one of the electrons will be lost when you bombard the alcohol containing this oxygen atom with very fast energetic electrons, and that results in the formation of plus radical. You can observe here, there are two electrons. One of the electron is lost, so the losing of electron is represented by plus in chemistry. That's why we have written plus radical plus two electrons. What if it is an amine? Say this is primary amine. Amines will have nitrogen as the heteroatom. Even the nitrogen will have a lone pair of electrons. When you bombard that with sufficiently energetic electrons, so one of the electrons is lost. Here there are two electrons on the nitrogen. Here you can see that one of the electrons is lost from the nitrogen, resulting in plus radical, and this is called as molecular ion for primary amine. And this is the case of unsaturated system. This, for representation purpose, we have shown alkene. There can be alkyne also. So here in the case of alkenes, it has got one pi bond and one sigma bond. So sigma bond, it is very difficult to remove, but still it can be removed. We can see that in the next example. But when you have got both pi bond as well as the sigma bond, usually electron from the pi bond is lost, so which is depicted here, plus radical here. Instead of a bond, you can write two dots. Two dots represent two electrons. Here one electron is lost, that's why we have written plus. So this is the formation of molecular ion in the case of unsaturated system. And this is the case of alkanes. So alkanes has got two types of sigma bonds. One is CC sigma bond, another one is CH sigma bond. It is easy to remove the CC sigma bond electron rather than CH sigma bond electron. So here CC bond is cleaved. Imagine instead of bond there are two electrons. By the contribution from both the carbons, dot dot, you remove one dot, it becomes plus. So this is the formation of molecular ion in the case of saturated system like alkanes. And now it is very clear for us that the energy required to remove an electron from the lone pair is very, very easy because they are readily available. So whenever you hit that with a fast moving electron, it is having the tendency to remove an electron. So lone pair requires very, very less energy compared to pi electrons. Pi electrons require less energy compared to CC sigma bond. So CH sigma bond requires more energy when compared to these three systems. So finally, to summarize, lone pair, in order to remove an electron from the lone pair, you need less energy compared to CH bond, because in CH we do not have either the lone pair nor the pi bond. So that is only sigma bond is there. Sigma bond, we know that it is very strong, but still because the energy of the electrons is very high that you are going to bombard, because of that the rupturing of the bond between CH takes place, but the energy required will be very, very more when compared to these three. This is the representation of for the formation of molecular ion for different classes of organic compounds. Now this is the diagram which shows the formation of the molecular ion. You can clearly see that M plus radical, and this is the mass spectrum of ethylamine. It is a primary amine. You can see that usually M plus is formed at the highest mass region. So you know that mass spectrum, it gives us the molecular weight of the sample. That's why whatever the highest mass, usually in most of the cases you are going to get, that will be the molecular ion. Then what will be the stability of this molecular ion? Stability of the molecular ion decides its relative abundance. Sometimes you will get very high intensity molecular ion peak. Sometimes you will get very, very low intensity molecular ion peak. Sometimes you will see that the molecular ion itself is absent. When you take up the fragmentation pattern, we are going to study one by one. So the abundance of the molecular ion peak can be increased with respect to the abundance of fragment ions by running the spectrum at very low potential. That is, by bombarding with low energy electron. Instead of 70 electron volt, you can reduce the energy maybe half or maybe 3/4 or maybe 1/4, and thereby you can increase the intensity of the molecular ion peak. It can be very small. If you want to increase this, then run this spectrum at very low energy potential. So this peak intensity may grow up rapidly. Then coming to the intensity of the molecular ion peak, you will see that the intensity of the molecular ion peak depends on the type of compound or the nature of the class of organic compound. Not all the classes of organic compounds have got the same intensity. Some will have very high intense peak, some will have low intense peak, some will have zero molecular ion peak at all. Usually, whenever there is a pi bond or whenever there is a conjugation in the molecular ion, then its intensity will be very, very high. Usually, the cyclic compounds will give very strong molecular ion peaks. It is because of the simple reason that when you break the cyclic compound, it does not result in the formation of two fragments. Rather, you will get only one molecule. Because of that, you are going to see very, very high intense peak in the case of cyclic compounds. Usually, intensity of the molecular ion peak can also be increased by the presence of heteroatoms with easily ionized outer shell electrons. Say, for example, if your sample of interest is highly branched, or if it is a tertiary alcohol, in such cases, molecular ion peak will be completely absent. Whereas in the case of primary or secondary alcohols, the molecular ion peaks will be very, very small. Though they are present, it will be very, very small. This is about the intensity of the molecular ion peak. Now we will take a look at different classes of organic compounds and their intensity. So here comes the intensity. It can be categorized into Three types: strong, medium, and weak. And these are the different classes of organic compounds. Say, for example, if your structure has got aromatic hydrocarbon, fluorides, chlorides, nitrides, amines, saturated cyclic compound, all such compounds and their derivatives will show very, very strong molecular ion peak. Say, for example, your structure has got aromatic bromide, iodide, conjugated alkenes, benzyl, benzoyl, straight chain aldehydes and ketones, acids, esters, amides, ethers, alkyl halides, all such classes of organic compounds, they will give very medium intensity ion, molecular ion peaks. Whereas if you take the next class of organic compounds like aliphatic alcohols, amines, nitriles, branch chain compounds, acids, esters, amides, ethers, and alkyl halides, in these cases, the molecular ion peak, though they are present, its intensity will be very, very weak. So this is the table which gives a rough idea like as to which class of compounds will give high intensity, medium intensity, or low intensity molecular ion peak. Based on that, you can decide whether the given compound belongs to this class of organic compound, or you have to check for the different another class of organic compound. So this intensity of the molecular ion peak decides at a first gauge about the, it gives a clue about the structure of the organic compound. Say, for example, in the case like if the molecular ion peak itself is absent, then you can say that the molecule will be highly branched, or it could be a tertiary alcohol. If it is very, very weak, then you can suspect that the molecule may be a primary alcohol or secondary alcohol. Like that, it have the intensity of the molecular peak definitely helps or aids in the structural elucidation of organic compounds. And this is about our molecular ion peak. The next item for the today's module is about the base peak. So molecular ion peak is different, base peak is different. We don't have to get confused between these two. What is a base peak? Whatever the highest peak, the longest peak or high intensity peak you see in the mass spectrum, that you should regard it as the base peak. Say, for example, this is the mass spectrum of methanol. In this methanol, there are several peaks. Each line represents a peak in the mass spectrum. Among all these lines, especially the peak at 31, m by z 31, you know that mass spectrum is plotted by taking m by z on x-axis and relative abundance or intensity on y-axis. When you plot such thing, you will see that many peaks will be observed. Among all the peaks, only one peak or two peaks sometimes will show very high intensity peak whose arbitrary is assigned as 100. So, and such a peak is known as the base peak. So, the largest peak in the mass spectrum corresponds to the most abundant ion or the most intense peak, and that is called as the base peak. You can clearly see here, this is methanol. When I subject methanol for bombardment with high energetic electrons, one of the electrons from the oxygen lone pair will be lost. That leads to the formation of molecular ion. So this molecular ion, because the electrons have got sufficient energy, this molecular ion will be undergoing fragmentation to form daughter ions. So first H will be lost from the CH3 minus H radical. That results in the formation of CH2 double bond OH plus. So you will see that in mass, usually the positively charged ions are formed, even negative and neutral atoms are formed, but they are not considered by the mass detector. They will be pumped out of the system that we have seen in yesterday's module. And this CH2 double bond OH plus having m by z 31, that is the base peak in this case. Why do we have base peak? This may be due to the presence of a pi bond. Because there is pi bond, there will be delocalization, and hence you will see that such peaks are going to be called as the base peak. Whereas this is the CH3OH plus, this is the one, this is the molecular ion. See here, molecular ion is 32, that means molecular weight, you can easily calculate 12 plus 3, 15, 15 plus 16 is 31, 31 plus 1 is 32. 32 is the molecular weight of methanol. See, 32 is given here. Molecular ion is different, whereas this is at 31 by losing only one proton or one hydrogen, and that is at mass 31, m by z 31, that is called as base peak. In this case, methanol, this is the molecular ion peak and this is the base peak. But in some classes of organic compounds, you will see that molecular ion peak will be the base peak, but it all depends on the particular class of organic compound. Not all classes of organic compounds will have both molecular ion peak and base peak as same. they will be different. But in rare cases that we will study in next modules, that you will see molecular ion and base peak both will be one and the same, will be the same peak. But in this case here, usually 90% of the compounds you will see that molecular ion peak is different and base peak is different. So that is about the base peak. Next item that we have got to study here is about metastable ions. Metastable ions. The name itself is giving you a clue that these are not so stable ions. Meta is say 50-50. Maybe it is neither stable nor unstable. So these are the ions which do not have much stability, and they are also appearing in the mass spectrum sometimes. Usually, when you take a mass spectrum, you will see that you are going to get beautiful straight lines, very sharp integrals, sharp peaks at definite integral values. You will see that the mass of this peak is 137, this is 123, this is 109, and this is 82. But sometimes you will see that a broad, diffuse, very low intensity peak, they appear at non-integral values, and they are called as metastable ions. You will see that here it is around 104. You can see that there is a broad hump like structure. It is very broad, which is very diffuse and very, very low intensity. And you can compare a peak. This is also a peak, definitely. Compare these two peaks. This is very sharp peak and this is a blunt peak. So this sharp peak has got a definite integral value 109, whereas this broad peak has got the m by z of 104.3, 104.3. That means it is a non-integral value. I can say that it is an integer. So usually metastable ions will have the non-integer values, whereas the stable ions, maybe molecular ion, the base peak, or the daughter ions, they will be very, very sharp in nature and they will have definite integral values. And those ions which are not stable enough, they appear as weak, broad, diffuse peak, and they are appearing at non-integral values. Such peaks are called, or such ions are called metastable ions. So how these metastable ions are formed? We know that in mass spectrometer, there will be a sample inlet. After that, there will be an ionization source. So if everything goes well, the sample undergoes ionization inside the sample's ionization chamber, and it will come out of the ionization chamber and it will enter into the analyzer. If everything goes well, then the peak will appear like this. But sometimes what happens, instead of the ionization taking place inside the ionization chamber, if it takes place outside the ionization chamber, then such ions will be recorded as metastable ions, because they are having different time, they appear at different time scale in the mass spectrum. So before they reach the detector, definitely the ionization will be taking place, but not in the ionization chamber. If everything goes well inside the ionization chamber, you will get very sharp peaks. But if the ionization does not take place inside the ionization chamber, rather it will take place outside the ionization chamber or between the analyzer, then you will get very broad, diffuse, low intensity peaks, and such peaks they appear at the non-integral values, and they are called as metastable ions or metastable peaks. If this reaction, as I said, M plus to M plus, small big M plus to small m plus, that is molecular ion undergoing fragmentation to form daughter ions. If everything takes place inside the source, then it is recorded as a daughter ion. You are going to get very sharp peaks. But if the above reaction occurs outside the source exists, that means outside the ionization chamber, but before arriving at the collector, then M plus is recorded as M metastable ion. Usually metastable ion is represented as small m star that we are going to see now. So in the mass spectrometer, you will see that there are two field-free regions. The first field it is called as drift region. The first drift region, usually it lies immediately before the electrostatic analyzer. You know that there is a sample inlet, there is ionization chamber, there are two analyzers. So one drift region will be before the electrostatic analyzer. The second drift region will be between electrostatic analyzer and magnetic analyzer. So an ion with charge E, after being accelerated through a potential V volts, will possess kinetic energy equal to EV, that is charge of the electron into voltage. If the reaction takes place in the second drift region, that means if the ionization takes place outside the ionization chamber, that is outside the ion source, then the daughter ions will have different kinetic energy when compared to the normal daughter ions. Thus, these daughter ions will not appear at the normal position in the mass scale. Rather, they will have different timeline. That's why they appear at the non-integral value. Say, for example, the normal daughter ion should have appeared at 104 because the ionization has taken place outside the chamber. That means there is a time lagging. So instead of appearing at 104, maybe that ion will appear at 105.2. So the presence or the appearance of such fractions, such non-integers, definitely give us a clue that it should be a metastable ion. Then how can we calculate the mass of such metastable ions? It is very simple. It can be calculated by using the equation m star is equal to small m square divided by capital M, where the small m star represents the mass of the metastable ion, small m represents the mass of the daughter ion, capital M represents the mass of the parent ion. So this is nothing but our molecular ion, this is daughter ion, and this is the metastable ion. We will take few examples to calculate the mass of the metastable ions. This is the first example. This is acetophenone. When you bombard the acetophenone with very high energetic electrons, so it becomes a molecular ion. The first step is not shown just for the convenience. The mass of the molecular ion here is 120. Usually in mass spectrum, you should write it as m by z 120. M by z refers to mass to charge ratio, and this is the molecular ion. So when you hit this molecular ion with the excess of energy, what happens? This methyl, it tends to undergo rupture here. When it undergoing rupture, you will see that there is a bond. A bond means there will be two electrons. One electron will be moving here, another electron will be coming on the methyl. So this becomes methyl radical, and this becomes triple bond because this oxygen will have another electron, this electron, this electron, and this electron, which will form a triple bond here. And this is m small m plus. That means this is the daughter ion whose mass is m by z 105. Here for the daughter ion, we won't write plus radical. Plus radical we write only for the molecular ion. For all the daughter ions, you should write only plus, because only positively charged ions are detected in the mass spectrometer. Now, in such a reaction, if you want to calculate the mass of the metastable ion, you have to go for the simple equation m star is equal to small m square by m. Here, small m is the daughter ion, capital M is the parent ion. Here, this is the parent ion and this is the daughter ion. The small m, this is small m whose mass is 105. So m square 105 times 105 divided by 120, that is capital M 120. When you equate this, we will get 91.8. You have to clearly observe here that the parent ion has got definite integral mass, daughter ion has got definite integral mass, whereas the metastable ion has got non-integral mass 91.8. You are going to get fraction. You will get fraction only if there is metastable ions, otherwise you will not get any fractions at all. Second example, we will take the case of toluene. In the case of toluene, you have toluene, you hit with very high energetic electrons, it will form molecular ion. This is the molecular ion, that means this is here plus radical. This H will be lost, so H is losing as a radical, it becomes CH2 plus. Now we have to remember that benzene ring with CH2 plus, this is called as tropylium cation. It will rearrange to form a 7-membered cyclic system. So here there are 6 carbons and this is 7th carbon. The ring opening takes place. When the ring opening takes place, the CH2 becomes a part of the ring. So instead of 6-membered, it becomes 7-membered ring. So in the 7-membered ring, the electrons will be continuously resonating, and that is called as tropylium cation or tropylium ion, whose M by Z is 91. Here in this case, this becomes the molecular ion. So this tropylium cation is highly unstable. So definitely it has to get converted into a stable product. What can be done? So from this tropylium cation, a 7-membered ring, a molecule of ethyne, that is C2H2 acetylene, will be lost. That results in the formation of a 5-membered ring whose mass is 65, and this is the daughter ion. So in this equation, this is the parent ion and this is the daughter ion. Now for such a reaction, if you want to calculate the metastable mass, we know the equation m star is equal to small m square by m, that gives out to be 65 small m is this, daughter ion 65 times 65 divided by capital M is 91. When you equate this, you will get a non-integral value of 46.4. Definitely it says that this is the mass of the metastable ion. Another example we will take, this is para-methoxyaniline or para-aminoanisole. In both way we can call this. So you heat this with electron to form a molecular ion, and this is the mass of the molecular ion, 123. So the process of fragmentation takes place now. The molecular ion will lose methyl to form a daughter ion. This is the daughter ion whose mass is M by Z 108. So this is capital M and this is small m. You can clearly see that there is a conjugation in this. As a result of conjugation, its intensity will also be very, very high. Now, for this reaction, if you want to calculate the metastable ion P, you substitute the values in this equation. M square small m is this 108 times 108 divided by capital M is 123. When you equate, you will get 94.8. Definitely it is a non-integral value, saying that this is the mass of the metastable ion. Now we will see that in what way these metastable ions are of very important. These metastable ions, they assist in the structural elucidation of organic compounds. Say for example, you will see that instead of a sharp peak, if you get a broadening, that broadening may be due to the reason that some of the excitation energy that lead to the bond breakage may be converted into additional kinetic energy. Because the molecule will get additional kinetic energy, so they will appear at different integral value, that is non-integral values. Then what is the significance of M star? Why we have to study this? This presence of metastable ions is for a very good evidence that the reaction takes place is a one-step process, and hence it is of mechanistic importance. Say for example, this parent ion, it's undergoing fragmentation to form a daughter ion. If you want to know whether it is a one-step reaction or two-step reaction, and if you see a metastable ion for this reaction, then definitely you can say that this is a one-step process. That's how this metastable ion is mechanistically very, very important, and also for the structural elucidation of organic compounds. Now we will try to solve some problems regarding the calculation of mass of the metastable ion, and also using, if metastable ion mass is given, you can calculate for either daughter ion or parent ion. If the mass of the daughter and parent ion is given, then you can calculate easily the mass of the metastable ion. Now we will see how best we can utilize this equation in order to calculate all those things. We will work out the exercise 1. The first problem: calculate the expected apparent mass of the metastable ion produced when M by Z 77 decomposes by loss of acetylene, that is C2H2, to M by Z 71. Clearly try to understand the problem. Here they are asking us to calculate the mass of the metastable ion, given that when the ion with M by Z 77 decomposes to give M by Z 51. So 77 is the highest mass, 51 is the lowest mass. Definitely it indicates that 77 should be the parent ion, 51 should be the daughter ion. Now we know the mass of parent ion and daughter ion. You can easily substitute that in the equation and can arrive at the mass of the metastable ion. How we do that? We know that M star is equal to small m square by M. M star is the, small m star is the mass of the metastable ion. Small m is mass of daughter ion. Capital M is mass of parent ion. Here small m refers to 51. 51 times 51. Capital M is 77 divided by 77. When you solve this, you are going to get 33.4. So 33.4 is the mass of the metastable ion for this particular reaction from 77 to 51 by the loss of a molecule of acetylene or ethine. Second problem: calculate the M by Z value for the normal daughter ion generated from the decomposition of PHCO plus a benzoyl cation. This is BNZOYL. Benzoyl cation with M by Z 105, given that a metastable ion near M by Z 56.5 is associated with this decomposition. So slightly different kind of problem. What they have given is, they have given the mass of parent ion They have given the mass of metastable ion and they are asking us to calculate the mass of the daughter ion. So when two parameters are known, the third one can be easily found out by putting all those terms in this equation. M star is equal to small m square by m. So metastable mass is 56.5. You put that here. M square, we don't know, question mark, divided by mass of the parent ion is 105. So 105. When you solve this, cross multiply this, you are going to get 77. Definitely 77 is the mass of the daughter ion. You can see that 56.5 they have already given. Don't get confused that always metastable ion mass will be asked to calculate. Sometimes these two will be given, this will be asked, sometimes these two will be given, this will be asked, sometimes these two given and this will be asked. So you have to be very careful when a question is given like this. So 77 is the mass of the daughter ion, which is having the definite integral value, and this is appearing at the non-integral value. So this is the third problem. You have to solve this by yourself. If at all you have got any problem, you can comment on the channel. So calculate the M by Z value for the parent ions that produce the following normal daughter ions and metastable daughter ions. So what they have given here, they have given mass of daughter ion and the metastable ion, 5 daughter ions and 5 metastable ions. That means each row corresponds to one problem. So 3, A, B, C, D, E. Not all the 5 parameters are for only one problem. There are 5 different problems and the third one. So using the mass of daughter ion and the metastable ion, you have to calculate the mass of the parent ion. You do it by yourself, simple cross multiplication, simple mathematics. So solve by yourself. So this is all about the metastable ions. The next item that we have to talk about in this module is about nitrogen rule. What is so special about this nitrogen? Why we do not have hydrogen rule, carbon rule, or oxygen rule, or phosphorus rule? Why only nitrogen rule? That we will see now. So nitrogen rule, it states that if a molecule contains an even number of hydrogen atoms, it includes 0 also, its molecular ion will appear at even mass value. If it contains an odd number of nitrogen atoms, it will form a molecular ion with an odd mass. It is very, very simple. If you see that the molecular weight of the sample is even, then the molecule may have even number of nitrogen atoms or 0, because 0 is also considered as an even number. So if the molecular weight is even, there can be even number of nitrogen or 0 nitrogen. If the molecular weight of the sample is odd, then the molecule will have odd number of nitrogen atoms. We will see by taking different examples. Here this is CH3OH. It does not have any nitrogen, that means 0 nitrogen. Its mass should be even. Let us see what is this mass. Methanol, 12 plus 3, 15. 15 plus 16 is 31. 31 plus 1 is 32. So 32 is the mass. 32 is a even number. Even number means there should be even number of nitrogen atoms or 0 number. Even means it starts from 0 to like that. Right? And this is phenol, C6H5OH. When you calculate the mass of this, 12 times 6, 1 times 5, 16 times 1, 1 times 1, it comes out to be 94. 94 is an even number. Definitely you can see that there are no nitrogens. So 0 nitrogen, or there can be even number of nitrogens. Now we will take up ammonia, NH3. There is 1 nitrogen. Definitely the mass should be odd in this case. Nitrogen is 14. 14 plus 3 is 17. 17 is an odd number. So this molecule has got odd number of nitrogens. Now this is hydrazine, NH2, NH2. Definitely there are 2 nitrogens, 2 is even. Its mass should also be even. 14, 14, 28. 28 plus 4 is 32. 32 is an even number and it has got even number of nitrogen atoms. This is C5H5N2. There are 2 nitrogens, meaning that the molecular weight should also be even. Definitely its mass is 94. So 12 times 5, 5 times 1, 14 times 2. When you work out, it comes out to be an even molecular weight compound, 94. That's why you can say that there are either 0 nitrogen or even number of nitrogen. This compound has got 2 nitrogens. 2 is an even number. And now we have to study why there is so special about nitrogen and not other elements in the periodic table. What is the basis for this rule? This table clearly sets the basis for this rule. These are different elements. This is the mass and this is the valency. First we'll take up carbon. Carbon mass is 12, valency is 4. both are even. 12 is even, 4 is even. So it is even, even. Take up the case of hydrogen, mass is 1, valency is 1, odd, odd. Take up oxygen, mass is 16, valency is 2, even, even. Take up sulfur, mass is 32, valency is 2, even, even. In all the four cases, CHOS, you will see that you will get either even number or odd number. Now take up the nitrogen question. Here, nitrogen has got mass of 14, that is atomic number 14, valency is 3. One is even, another one is odd, and this is an exception. Because of this exception, it has got a special rule called as nitrogen rule. You will see that when we go for solving the composite problems, and if you find that molecular weight of the sample is even, you can definitely predict that there can be either zero nitrogens or even number of nitrogens. If the molecular weight comes out to be odd, then you can definitely tell that the molecule has got at least one nitrogen in it. So this is the basis for this rule, and this is all about nitrogen rule. This nitrogen rule also is highly helpful in the structural elucidation of organic compounds by predicting whether nitrogen is present or not. If at all it is present, how many are there, either in even number or in odd number. And this is all about the nitrogen rule. The last item for today's class is the ring rule. This already we have studied in our previous classes when we solved the problems, but still we have to study under mass spectrometry. What is this ring rule? A ring rule, it states that, or it says that how many number of unsaturated sites are there, or how many rings are there within the molecule. Unsaturated sites refers to double bond or triple bonds. These double bond, triple bonds are also included with the rings in the compound. So if you know the equation to calculate this ring rule is nothing but double bond equivalent or RA relative abundance that we can easily calculate by using this ring rule. So how can we state this ring rule? The number of unsaturated site R is equal to the number of double bonds and or rings in the molecule. The ring rule for the molecule CaHbNcOD may be expressed as R is equal to A plus 1 plus C minus B by 2. Here A refers to carbon, B refers to hydrogen, C refers to nitrogen. So you just have to remember this formula, R is equal to A plus 1 plus C minus B by 2. You have already learned this while solving the problems, but as far as the syllabus is concerned and the mass spectrometry, we have to study this. Now we will take different examples and we will apply this ring rule. Take this diethyl ether. Now for this, they've already given the molecular formula. If molecular formula is not given, say for example, in this case, the structure is given, then you have to convert this structural formula into molecular formula and then substitute those numbers in this equation. So here C2H5O, C2H5, R is equal to A plus 1 plus C minus B by 2. Here A is carbon. How many carbons are there? 4 carbons plus 1, 0. We do not have any nitrogen. That's why 0. And how many hydrogens are there? 5 to 5. 5 plus 5 is 10. So 0 minus 10 by 2. 4 plus 1 is 5. 5 minus 5 is equal to 0. Definitely diethyl ether has not got any unsaturation. It has not got ring also. That's why the ring rule or double bond equivalent is coming to be 0. So if you say the double bond equivalence is 0, then you can clearly straight away say that unsaturation is absent in the compound, ring is also absent in the compound, and it may be an aliphatic chain system. And definitely this diethyl ether is an aliphatic compound. And now C6H6. C6H6 is benzene. So we know that R is equal to A plus 1 plus C minus B by 2. Substitute here 6 carbon plus 1 plus 0 nitrogen minus 6 hydrogen by 2. 6 plus 1 is 7. Minus 6 by 2 is minus 3. 7 minus 3 is 4. So benzene will have 3 double bonds plus 1 ring. A ring is also considered as 1 double bond. That's why it is called double bond equivalent. So 3 plus 1 is 4. Definitely it is 4. Whenever you get 4 double bond equivalent, then you can easily predict that the compound may contain a benzene ring. So it should be a derivative of benzene. This is C6H5CH3. This is toluene. We know that toluene also has got a benzene ring. But how many double bond equivalents? If you want to know that, you have to substitute that in this formula. So here there are 7 carbons, 7 plus 1 plus 0 nitrogen, 0 minus. So is 5 plus 3 is 8 hydrogen, 0 minus 8 by 2. 7 plus 1 is 8, minus 8 by 2 is minus 4, 8 minus 4 is 4. So definitely benzene ring CH3, that is toluene. Benzene ring will have 3 pi bonds plus 1 ring, that is also considered as 1 unsaturation. So definitely DBE will be 4. This is about the ring rule for toluene. And this is case quinoline. And this quinoline, we have to, they have given only the structural formula. Convert the structural formula into molecular formula. How many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons. So 9 plus 1 plus, there is 1 nitrogen, 1 minus hydrogen, we have to calculate. 1, 2, 3, 4, 5, 6, 7. So 1 minus 7 by 2. 9 plus 1 is 10. 1 minus 7 by 2 is minus 3. So 10 minus 3 is 7. So there are 7 unsaturations. How such 7 unsaturation? You can clearly see here. Here 3 and here 2. 5 double bonds plus 2 rings. 1 ring, second ring. 5 plus 2 is 7. Definitely the double bond equivalence is 7 for the quinoline. So this is how ring rule is also highly helpful in the structural elucidation of organic compounds when we want to know how many rings are there, how many unsaturations are present in the system. So this is about the ring rule. Thank you very much.